Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to your favorite Shridevi classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in our basic electrical engineering and class 12th physics in chapter alternating current circuits, we'll understand root mean square value or RMS value of alternating current, and we'll understand how mean of the square when rooted gives us a value 1 by root 2 times amplitude of sinusoidal quantity, and this RMS value is equivalent working capability of alternating current in terms of DC value. We'll also derive a relation of RMS magnitude with peak magnitude, and we'll understand RMS value of other periodic alternating signals and rectified output. So let's start study of RMS value of alternating current. A standard sinusoidal alternating signal starts from 0 instantaneous value at time instant 0 and increase in positive direction with non-linear rate, whereas a generalized sinusoidal signal can start from any positive or negative value at t equal to 0 position and will have the same type of variation as that of standard sinusoidal signal, but with a pre-specified phase difference. Such alternating signals, whether they are current or voltage, their instantaneous magnitude continuously change with respect to time, and they also alter their direction or voltage change its polarity after every half cycle. The instantaneous magnitude of sinusoidal signal is expressed in terms of peak magnitude or amplitude, angular frequency, and phase angle, and when time changes as per its phase angle, its initial value change its magnitude and direction as per this mathematical trigonometric expression. The peak magnitude of alternating signal, whether it is a standard sinusoidal signal or a generalized sinusoidal signal, is a instantaneous value only, and that exists only for a very small, negligible small time instant. Now, peak magnitude of applied sinusoidal voltage decide voltage withstand capacity of insulator used in electric device or installations, or this peak magnitude of voltage got a relation with shock conditions when electricity is used by human beings, but in other conditions or in calculation, such peak magnitudes which are expressed in front of this sine function as multiplier got little relevance. Also, the time varying alternating current got symmetrical positive and negative half cycle. So, full cycle charge transfer capability of this alternating current or full cycle average value of such currents are always 0. So, average value or charge transfer capacity is also not very relevant. So, neither peak magnitude or amplitude of sinusoidal signal or average value of sinusoidal signal is relevant in mathematical analysis. In fact, in place of charge transfer by alternating current, we are interested in working capability of alternating current or power values of alternating current. When alternating current flow in a circuit, the drift of electron reverts its direction after every half cycle, but whatsoever the half cycle part of alternating current or drift motion direction of electrons, the collision among electron produce heat energy from electrical energy and perform work just like flow of direct current. So in alternating current, though the direction of current alter after every half cycle, but the phenomena of heat production remains the same as it is by collision among accelerated drift moving electrons. The effective or working capacity of sinusoidal alternating current or root mean square value of alternating current is obtained by comparing heat production capacity of alternating current in resistance by heat production of steady DC current in the same resistance with the same time. For comparison, time varying sinusoidal alternating current and steady DC current both are allowed to flow through the same resistance for the same time, and that time for comparison is considered as time period of one entire cycle. As the same cycle is repeated afterwards, so comparison for one time period and for longer time duration would give the same result. Voltage across any resistance is defined as work done per unit charge, and when Q amount of charge is passing through any resistance having V voltage across it, the total amount of work done is product of voltage and amount of charge, and time rate of work done per unit time is known as power, and power becomes voltage multiplied by rate of charge flow, and rate of charge flow is current. So product of voltage and current is power in any resistance, and if we use Ohm's law, V is equal to IR, the power become I square R, and in case of steady DC current when flow through a R ohm resistance, the amount of power in watt is constant and given as I square R. And for time varying sinusoidal alternating current, as current instantaneous value change with respect to time, the power is also variable, and power as per square of current varies and given as small I square R, where the small I is instantaneous value of time varying alternating current. So DC power is steady constant and AC power is proportional to square of current and is variable, as current magnitude is variable for alternating sinusoidal current. In an ideal DC current, the magnitude of current remain constant with respect to time, and power of DC current proportional to square of current is also constant in magnitude with respect to time, whereas sinusoidal alternating current not only change its magnitude, also change its direction, and power in alternating current supply proportional to square of instantaneous current got this Brown wave variation as proportional to square of instantaneous current, and square of negative instantaneous current is also positive, and we'll find that for one cyclic variation of alternating current, the variation of power would have 2 cycles. So the frequency of variation of power signal got twice the frequency of exciting current. If current is of 50 Hz frequency, the power signal will have periodic variation frequency of 100 Hz. The standard sinusoidal current I equal to Im sin omega t change its magnitude as well as direction, and when this current passes through a resistance of R ohm, the power in that resistance by flow of alternating current proportional to square of instantaneous current varies as shown in this Brown wave proportional to square of instantaneous current, and since square of a negative quantity is also positive, so power will not change its direction, but its magnitude will change as per the change in instantaneous current. And in this variable power of alternating current in resistance, elemental work done in a small time interval dt is given by differential product of instantaneous power and elemental time, and as per Joule's law, instantaneous power of alternating current is I square R, where this small I is time varying instantaneous alternating current, and as current changes, power in resistance changes as per Brown relationship, and total work done in a considerable time duration can be obtained by integration of elemental work, and elemental work is product of power and time duration, and power is I square R. Then integration of I square with respect to time for given time duration gives us total work done by alternating current. Now the work done of alternating current is compared with the work done of steady DC current for one cycle time duration, as the same cycle is repeated. So a comparison of one cycle or one time period duration will be used for any long considerable other time. To find out equivalent working capacity of time varying sinusoidal alternating current in terms of steady DC value, given sinusoidal standard alternating current I equal to Im sin omega t and a steady direct current, both are compared for equivalent power capacity by equating the heating work done by flow of both steady DC current and time varying alternating sinusoidal current in the same resistance for the same time duration, and for comparison's sake we'll consider time duration equal to time period of one standard sinusoidal current. So for same power capacity of alternating current and steady DC current, work done by steady DC current and work done by time varying alternating current will be the same in the same resistance for the same time period, and work done of alternating current is obtained by integration of elemental work done contribution. For study DC I current, the power is I square R, and in time duration of one cycle period, time period capital T, work done by DC is I square RT, and work done of AC current is integration of elemental work done. And for instantaneous current small I, the power is I square R, and for that time varying instantaneous power, amount of elemental work done in elemental dt time is dW, and integration of dW for one standard time period of alternating current starting from 0 time instant to 1 time period is work done by AC. This R being constant when brought out of integration will get cancelled out with R of DC power, as DC current and AC current both flow in the same resistance for the same time period. And if we simplify the relation, the square of DC current becomes 1 by T times integration of square of instantaneous current with respect to time. Here this square of instantaneous current is integrated for one time period and divided by the same time duration, so it is a mean of square of instantaneous current. And if we take root of both sides, then study DC current, which perform same amount of work as performed by alternating current in the same resistance in the same time, will become square root of mean of square. So this quantity, which is integration of instantaneous current square divided by the time duration mean of square, is square rooted, become root mean square value. And we can say root mean square of alternating current is that study DC value which perform same amount of work in the same resistance in the same time duration which is performed by this alternating current. So RMS value of alternating current is equivalent working capacity of alternating current in terms of DC value. So square root of mean of square of instantaneous current or root mean square of alternating current is that study DC current which perform the same amount of heating work in the same resistance in the same time. We can say RMS value of alternating current is equivalent working capability of alternating current in terms of DC value, and this DC value is also called as effective value of alternating current. And if we replace the time varying instantaneous current I equal to Im sin omega t in this RMS value expression, then this become root of mean of Im square sin square omega t. So when in this RMS value calculation instantaneous current is written as Im sin omega t and square root, this Im square being constant brought out of integration. And for integration, as sin square omega t is not directly integratable, this is mathematically manipulated as 1 minus cos 2 omega t by 2. And now this mathematical expression can be integrated in two parts. 2 being constant can be brought out of integration, so Im square by 2t is a constant, and one integration is 1 times dt, and second integration is integration of cos 2 omega t with respect to dt. Now the integration of dt is t with limit starting from 0 to time period t, and integration of cos 2 omega t is sin 2 omega t by 2 omega, and limit of integration would be placed after integrated results as starting time instant and final time instant, one time period. Now in this variable t, once we put end limit of variable, and with sign change we put start limit of variable. Similarly this sin 2 omega t, and with 0 this becomes sin 0. Now omega t is 2 pi radian or 360 degree, which is equivalent to 0. So 2 time omega t is also 0, sin 0 is 0, and when 0 subtracted from 0, this results become 0, and this t and t will get cancelled out, and when we take square root, the RMS value comes as 1 by root 2 times peak magnitude or amplitude. So amplitude of sinusoidal current when divided by 1.414 or root 2, it gives 70.7% value, or peak amplitude multiplied by 0.707 gives us RMS value, or that study DC value which perform the same amount of heating work in the same resistance in the same time as performed by this standard sinusoidal alternating current. So RMS value is 1 by root 2 times peak value, and this mathematical expression is often derived in our examination. Standard sinusoidal alternating current is a time varying quantity, and heating power proportional to square of this instantaneous current as shown by this brown curve is also a time varying quantity, and mean of this brown is this steady value, and this steady effect is produced by this blue current, and this blue value of current is RMS value of current, and it is 1 by root 2 times of peak value or 70.7% of amplitude or peak magnitude of alternating current. So a sinusoidal current if got peak magnitude 10 ampere, then its equivalent steady DC current working value is 7.07 ampere. So this sinusoidal alternating current of 10 ampere peak value and DC current of 7.07 ampere current both produce same amount of heating work in the same resistance in the same time. We usually specify, represent or measure all alternating current or voltage signal in terms of their RMS value. For all calculation and analysis purpose, all alternating current and voltages use their RMS value or effective value. When we mention any alternating current as current of 5 ampere magnitude, then this 5 ampere magnitude is RMS value of that current or effective value of that sinusoidal alternating current. If we say domestic Indian power supply got a magnitude of 220 volt, then this 220 volt is RMS value of sinusoidal domestic Indian electric voltage supply. Now amplitude or peak magnitude of alternating signal is root 2 times its RMS value, and for Indian domestic supply having RMS value 220, its peak magnitude is root 2 times or 311 volt. So this sinusoidal alternating voltage for one particular time instant for a very brief negligible small time duration will attain or reach peak magnitude or amplitude 311 volt. So all electric appliances or installations working on 220 Indian domestic supply should have a voltage withstand capacity of 311 volt, as 220 volt RMS value attain at one instant its peak magnitude or amplitude 311 volt, and at that very instant insulation should withstand this voltage. We have given two electric supply. One is 220 volt DC obtained from a battery bank, and other one is domestic alternating electric supply of power system of 220 volt RMS value. We have two questions. Out of these two, DC and AC, which will perform more work and which will produce stronger or more dangerous electric shock? We know RMS value of alternating current is that DC value which perform the same amount of work. So 220 volt RMS value of AC and 220 volt DC will perform the same amount of work. So working capability of 220 volt DC and 220 volt RMS value of AC is the same, but DC voltage always remain at steady magnitude, so its shock is also corresponds to 220 volt value, whereas sinusoidal alternating voltage will attain its peak magnitude or amplitude once in positive direction and next in opposite polarity direction at particular instant, and at those instants its value is root 2 times its RMS value. For 220 volt it is 311 volt. So at that very instant it produce stronger or dangerous electric shock. So for same working capability, 220 volt RMS AC is more dangerous than 220 volt DC supply. In laboratories for test and research work and in industries and other positions for commercial work, alternating voltage and current cannot be measured by moving coil instrument, which measure full cycle average value, and full cycle average value of alternating current or voltage is 0. So moving coil instrument show 0 reading for alternating voltage and current, and for measurement of alternating voltage and current we use either hot wire type of measuring instrument or moving iron type of measuring instrument, and both hot wire type and moving iron type instruments have a deflecting torque mechanism which produce a deflecting torque proportional to square of instantaneous current value, and in that case, even though current reverses its direction after every half cycle, the torque proportional to square of that current remains in the same previous positive direction. In these measuring instrument with moving mechanism, we use phosphor bronze spiral springs, and against deflecting torque they produce restoring controlling torque to get balance position, and amount of control torque produced by phosphor bronze spiral spring is directly proportional to amount of angular displacement of moving mechanism at final equilibrium position. Controlling torque and deflecting torque become equal and opposite to each other, and damping used in instrument produce a steady position of pointer on scale to show amount of deflection corresponding to current, and that gives us final reading of current to be measured. At steady equilibrium of deflecting torque and controlling torque, the position of this pointer on scale gives us a reading of measured alternating current, and at that equilibrium the deflecting torque proportional to square of current become equal to controlling torque proportional to amount of deflection in moving mechanism, and final equilibrium deflection become proportional to square of current, and mean value of this square current correspond to RMS value, and we could measure RMS value of alternating current by this way. But during this measurement, since relation of deflection as square of instantaneous current is a non-linear relation, so our measured voltage scale become non-linear, and scale is initially cramped for smaller values, and later on for final scale values it is extended. Apart from sinusoidal alternating current, during studies we have to study some periodic wave such as square, triangular or sawtooth, or some rectified output such as half wave rectified output or full wave rectified output are analyzed, and we have to find out their RMS or effective value. Then RMS value of square is the same as its peak magnitude, whereas RMS value of full wave rectified output and sinusoidal alternating current is the same, Im by root 2. For sawtooth, RMS value is 1 by root 3 of amplitude or peak value, and for half wave rectified output, the RMS value of output is 1 by 2 times of peak magnitude, and we can write as Im by root 4, and we can remember these RMS value as Im divided by root 1, Im divided by root 2, Im divided by root 3, and Im divided by root 4, and root 4 is 2. So for square, RMS value is Im. For sinusoidal and full wave rectified output, RMS value is Im by root 2, and for triangular and sawtooth it is Im by root 3, and for half wave rectified output it is Im by 2. We hope this beautiful learning video has explained each and every aspect of RMS value of alternating current. You could now derive the relation of RMS value with peak magnitude as Im by root 2. You now understand that RMS value of alternating current is that DC value which perform same amount of work in the same resistances for the same time. Our other learning video of the same playlist are equally useful to enhance your subject understanding and exam score, and if you need exam centric notes and doubt clearing online classes from this channel, do join our YouTube membership. Happy learning, have a nice time, thank you very much.